Okay. So what we've seen so far is how to integrate individual trig functions. But what about if you've a couple trig functions? How do you integrate something like this? Integral of sine cubed x cos to the fourth x. And of course, just for notation, that's the same as saying sine x, everything cubed, cos x, everything to the fourth. Well, it turns out they basically just use algebra tricks to get something that we like. And then usually, but not always, we just wind up with a substitution as the basically last step. Okay. However, as part of the tricks that we have to do first, you're going to need some of your trig formulas. So these are the trig formulas that you're going to need. So I just have them here for reference. So we have first are the three basic trig identities. So everyone should know the first one by heart, and then the other two should ring a bell. Next, we have versions of the double angle formulas. So I'm going to call these the cos 2x formulas, because sometimes we'll be dealing with the cos squared, sometimes we'll be dealing with sine squared. I'll just call them the cos 2x formulas. And then you also need, we'll also briefly need these formulas when you have sines and cosines of different angles. We'll use that briefly. We'll come back to it later. Okay. Also, we just need to remind ourselves of the derivatives of all six trig functions. So just for handy-dandy reference, I wrote that down here. Okay, now let's use this and get to work. So that integral that I just showed you, integral of sine cubed x cos to the fourth x. To solve this, like I said, we're going to use substitution, but first we have to get it ready. So what do? Let me take you on a journey. I rewrote this in a very strange way. What did I do? I pulled out one of the sine x factors, and I put it at the end. Okay? Next, I take that sine squared x, and I rewrite it as 1 minus cos squared x. Next, distribute. So you wind up with cos to the fourth x minus cos to the 6x times sine x dx. And now what do?
Subtract them. Oh, sorry.
Substitution. And what's the u?
I don't know what.
What's your u?
No, cosine. The whole thing.
What's your u? What's your du?
U is sine.
I'll try sine x.
Yeah, u is
dx
sine,
to
so
be
you get
dx.
cosine to be u is sine, so you change it
I'll
to
guess
cosine.
cosine x.
U is sine.
Where's the derivative just sitting by itself?
Sine x.
Sine x dx. So what's your u? Cosine. So replacing sine squared x with 1 minus cos squared x gave us an expression that was entirely in terms of u, and then moving that single sine x to the end gave us our du. So you have to be careful because u equals cos x du obviously is negative sine x. You have to just track that sign. So I'm going to take that negative from the du and I'm just going to put it in front. And then you just have u to the fourth minus u to the sixth du. So if you integrate this, you get this, and I've also distributed the negative. So negative u to the 5th over 5 plus u to the 7th over 7. And then we put it back. Negative cos to the 5th x over 5 plus cos to the 7th, cos to the 7 x over 7. And plus c. And as you guys know, cos to the 5th x, you can also just write this as cos x to the 5th. Either one is fine. In textbooks, you'll always see the first one, but either one is fine. Okay. So I hope you can see that all this is just one extra trick that we need to do. Does everyone kind of see the trick and make sense? Okay. So what about this one? Integral of sine squared x cos to the 5th x dx.
We change the sine squared x to cosine minus 1 minus cosine.
So do we? That's the question.
No,
Turns out, what do you think will be the u and what do you think will be the du?
U be cosine. I mean U.
You'll be cos.
Either way.
And then what's going to be your du?
If you take the sine
There is
and
none.
cosine.
I would do sine squared
Sine
x dx as du, because then we can use identity to rewrite that, and then we're just integrating. Now cosine, well, I would only.
So it turns out that what we're going to pull out
It's cosine.
is a cosine.
Oh,
There's no reason to have that. Because then you have cosine squared x, cosine squared x. And then
Right. And cos to the 4th x is just cosine squared squared. So you get sine squared x, 1 minus sine squared x squared with a cos x dx. And now, what's going to be your u? What's going to be your du?
U sine.
U is sine.
U is going to wind up being sine x, and your du will be cos x dx once you multiply everything out. Boom. Okay. So now once you do the sub, it's very easy. So what you're probably wondering right now is, well, in the first one we pulled out a sine x, and the second one we pulled out a cosine x. How can I possibly know when to do which? And the secret is the power. Notice that we need an odd power, so that when we pull out a sine, as in the first one, or a cosine, as in the second one, there is a cos squared u or sine squared u, or a power of it, to replace. So let's take a look. So in the first one, sine cubed, so you can pull out a sine. In the second one, cos to the 5th, so you can pull out a cos. And still have something squared left over.
So you have to make it an even number the power.
After pulling out the one factor, yeah, you need an even power because it needs to be sine squared or sine squared squared or sine squared to the 3rd or something with sine squared that you can multiply out, or cosine squared. Okay, so what if?
they're both even.
What if they're both even? Then you have to use a different formula because this trick's not going to work. So what about the integral of sine squared x cos squared x? Well, then we use those cos 2x formulas. Sine squared is 1 minus cos 2x over 2, and cos squared is 1 plus cos 2x over 2. Right. So now we have to do some more algebra manipulation. So I'm going to take that the over 2 and the over 2, and I'm just going to pull that out. So I'm just going to get 1/4 in front. And then 1 minus cos 2x times 1 plus cos 2x
Square.
gives me 1 minus cos squared 2x. Okay. So what do we do with this? Well, once again, we've got a cosine squared. So, well, yes, it is sine squared 2x. That's true, but that doesn't. But we don't know how to integrate sine squared directly. So what would we do? We just use one of the cos 2x rules again. Now I didn't change it over to sine squared, but you could. I just left it as cos squared, and I said this is 1 minus this. But I want to bring your attention to something. What was the old angle in the cos squared? So what's the new angle in the formula? What happened to the angle? When you apply this formula, what happens to the angle? It doubles, right? So even though the formula is written in terms of x, we should think of it being in terms of u. So if we have cos squared of 5x, then what would that be equal to?
Cos squared of 10x.
1 plus cos of 10x over 2. So that rule always works regardless of what the angle is. You just have to double it. Okay. So now if we use some algebra to tidy this up, I just want to get the cosine by itself. So you wind up with 1 minus a half plus cos 4x over 2. So it gives you this. And then I'm just going to pull out that 1/2 as a factor. I'm just going to pull it out. And I'm going to write 2 separate integrals. So long story short, the first integral,
There's supposed to be a 4.
It's supposed to be 1 minus half, right? Not half minus half.
no, because there's a 1 in front, and then there's a minus a half from the fraction. So 1 minus a half
Yeah.
gives you a half.
But it says half minus half.
Yes, because it's cos 4x over 2. I'm just writing it as half cos 4x.
How did you get an 8 inside? Oh,
So-
okay, I see.
Yes. So then you just do 1/4 times a half, and it gives you an 1/8 in each case. Now, what's the integral of dx? It's the one that's so easy, you might get it wrong. It's like saying the integral of 1. So it's x. Okay. Now, so that's the first integral. That's done. What about the second integral? How do we do the second integral?
U equals 4x.
Yeah.
Yeah.
This is just the integral of cosine. It's very easy once we stop worrying about the 4x. And when you stop worrying about it, you just do a substitution.
Negative sign. Negative 4 sign.
U equals 4x, du equals 4dx. So that just gives you, and once you swing the 4 here, that'll give you the integral of 1/4 cos u du, with that 1/8 still in front. So you just get this. 1/8 x minus 1/32 cosine of 4x plus c. So when you have even powers, so when you sine and cosine and you have even powers, you have to use the cos 2x formulas. And how many times do we have to use the cos 2x formulas in this problem? We had to use it on 2 different steps. Okay.
I have a question.
One more question.
Here it's integral of cosine should be
Sorry, let me fix that. A little sleep.
with an x.
Okay. sorry about that. Integral of, oh no, that's a negative there. The integral of cosine, of course, is sine. Haha. Okay. Okay. So, when you get even powers, you just keep replacing using cos 2u formula until you get something you can integrate, like we did here. Okay. So that covers what to do with integrals that have sine and or cosine in them. Even powers, odd powers. What about other trig functions? Turns out we can do tricks like these with other trig functions as well. Integral of secant to the 4th x tan squared x. What do you do? So once again, we need to figure out what will be the u, what will be the du, what function gets replaced. So what are the possibilities? What could u possibly be? You could be secant x or you could be tan x. That's what we're assuming. So if it's secant, if u is tan x, then what's your du? Secant squared x dx. Now if u is secant x, what's your du? Secant x tan x dx. The only thing is we just have to, it's just going to be one of those two. Now it turns out in this case,
Can we do like tan squared x equals to secant squared x minus 1?
yeah, that's not helpful. Turns out in this case, we're going to pull out a secant squared x. So that's going to be the du. What happens when we do that? Well, we've got a secant squared x, which we can replace with a tan squared x plus 1. And after you multiply it out, it's very clear. Your u is tan x, and your du is secant squared x dx. So now you just have integral of u to the 4th plus u to the squared du. And that gives you u to the 5th over 5 plus u to the 3rd over 3. And then we put it back, and you get tan to the 5th x over 5 plus tan to the 3rd x over 3 plus c. So why did it work out this way? So notice that we need an even power of secant u in order to pull out a secant squared and then have an even power of secant left to convert to tan squared plus 1. So what's different with sine and cosine, you're just pulling out a sine or a cosine to be your du. But here you need to pull out a secant squared if you want that to be your du. So that's why you need to start with it. For secant, you need to start with an even power.
You have to know the relationship between the two functions.
You have to know the relationship between the two functions. That's exactly it. For the whole day, that's exactly it.
Professor, how come we can't, like,
Okay. So now, as you can imagine, we're going to look at the other case. So here we've got the integral of secant cubed x tan cubed x. So what are we going to put to the side? A secant x tan x dx. So in your head, you should be guessing, based on that manipulation, what's going to be the u, what's going to be the du. So the next step is to take tan squared and replace that with secant squared x minus 1. And now we can multiply that out. You get secant to the 4th x minus secant squared x times secant x tan x dx. And now, what's your u? Secant x. What's your du? Secant x tan x dx. There you go. So you get the integral of u to the fourth minus u squared du, and that very simply is u to the fifth over 5 minus u cubed over 3, which is just secant to the fifth x over 5 minus secant cubed x over 3 plus c. Okay, so how did we know that this one was going to work out? Notice that we need to have an odd power of tan x to pull out a secant x tan x, and then have an even power of tan x left over to replace with a power of secant squared x minus 1. So here with tans, we're back to needing odd powers. So what if you don't have these things? Other cases, we're going to need various techniques. So anytime you see various techniques, I'm not going to lie, you should be a little worried, because that means you have to figure it out. So I'm going to show you these, but keep in mind, this is going to be on the harder side, because you're going to basically be figuring it out as you go, and there's no like one step in the beginning. So let's take a look. Integral of secant cubed x dx. Okay. So we're actually going to pull out, we're going to split up the secant x and the secant squared x, and we're going to make that our u and our dv. So that means du is secant x tan x dx, and if dv is secant squared x dx, then v is just tan x. Okay, well, what does that give us? So this equals secant uv, so secant x tan x, minus the integral of v du, so minus the integral of tan squared x secant x dx. Okay. Well, what do we do now? Okay. Yeah, we'd like to find the integral of that. So what we're going to do is turn tan squared into secant squared x minus 1. Just manipulation, manipulation, manipulation. And then what happens? Well, now we have to multiply it out, and what do we get? So you get integral of secant cubed x, and then minus the integral of secant x. Well, something amazing happens. We have the original integral that we started with. So the integral of secant cubed x dx equals secant x tan x minus integral of secant cubed x dx plus the integral of secant x dx. Integral of secant x dx, we recently learned how to do that, so we know that. So all that's left is to solve for the original integral as its own expression. So you get this. Therefore, the integral of secant cubed x dx equals half of that whole thing. This is a hard problem. Okay, now, so what about another one? So we said we want odd powers of tan. What if we've just got an even power of tan by itself? What do? We can rewrite it as secant squared x minus 1. And now what? Split it into two integrals. The integral of secant squared x is tan x. The integral of 1 is just x. That's an easy one. Which is, and I mentioned this earlier, you can't always tell just by looking at the original integral. You can't tell immediately if it's going to be a hard problem or an easy problem. And it's not always, as you can see here, immediately obvious what technique you're going to use. So that's why I talk about indicators. That's why I say you're sometimes just going to have to try things. So there are certain kinds of integrals that are easy. If the integral looks like this, do that, and the problem will finish itself. But there are others that are going to be a little harder. Okay. So, so far we talked about integrals with powers of sine and cosine. Talked about integrals with powers of secant and tangent. Guess what's left? Integrals with powers of cotangent and cosecant. But as was mentioned earlier, the relationships between the formulas relating cosecant and cotangent are really, really similar to the formulas relating secant and tangent. So it turns out all the tricks are basically the same. So for example, integral of cosecant to the fourth, cotangent to the fourth. Well, which function is like which function? So cosecant is like which one and cotangent is like which one? Cosecant is like secant, and cotangent will be playing the role of tangents. So what do we have that we like?
Equal powers. Even powers.
An even power of which one? Which one do we like? Do we like, what did we see before? Do we like even powers of tan or even powers of secant? I think it was secant. Right. We like even powers of secant. So in this case, we like an even power of cosecant. Oops, too far. Right. So we like that even power of cosecant. We're going to pull out the cosecant squared x. Step 1. Step 2, we're going to rewrite the cosecant squared using the formula. So now you have to know that cosecant squared x equals 1 plus cotangent squared x. And now multiply out. Cotangent to the fourth x plus cotangent to the 6x times cosecant squared x dx. And now, what's your u? What's your du? U is cotangent x. And you have to remember what the derivative of that is. Negative cosecant squared x. You have to, so all the formulas are almost the same. You just have to remember where those negatives are. So I'm going to take that negative in the du, and I'm just going to stick it in front as a constant. And you get the integral of u to the fourth plus u to the sixth du. Easy integral. I'm also going to distribute the negative, so you get negative u to the fifth over 5 minus u to the 7th over 7, which is just negative cotan to the 5th x over 5 minus cotan to the 7th over 7 plus c. And cosecant cotan, in this case, we liked the fact that cosecant was an even power and u was cotangent. So what's the other case going to be? If for cotangent we have an odd power, and then our u is going to be cosecant. Exactly. And again, just follow the pattern, and it works in the exact same way as secant and tangent, but just watch out for that negative sign. Okay. One more type of trig integral that we can do, involving mixed angles with sine and cosine. this one's kind of nice because as soon as you see sines and cosines and mixed angles, you know exactly what it has to be. You have to use one of those mixed angle formulas. So just as a quick reminder, what were the mixed angle formulas? There you go. So we've got mixed angle formulas for sine and cosine, sine and sine, cosine and cosine. Okay. So this one was sine and cosine. So we need the formula half times sine of the difference plus sine of the sum. And that's it. So half times sine of the difference, which is 3x, plus sine of the sum, which is 7x. And this is now a very easy integral to do. So the integral of the sine function is negative cosine. But what's the one thing that you kind of have to be careful about? You have to be careful about your constants. When you integrate sine 3x, you do not get negative cos 3x. You get negative cos 3x over 3. Now, if you see that immediately, great. If not, then what should you do to make sure that you do that integral properly? Do a substitution. U equals 3x, and then your du equals 3 dx. Now, of course, that 3 isn't there, so what you really have is 1/3 du equals dx, and that's where the 1/3 comes from. So at a certain point, you'll get so used to doing these integrals that you'll just say, oh, sine 3x, that's just going to give me a 1/3. And then you can just do the integral like that. What you're basically doing there is you're doing a substitution, mental shortcut. Don't do the shortcut until you know what you're doing. And then I just straightened out the constants. I made it one nice expression here. One last technique that I'll call a bit of advice. So I'll say here's the most useful other technique. If you're having trouble with an integral, you're not sure which technique to do, and sometimes none of the situations that you've seen so far apply, convert to sine and cosine and hope for the best. For example, integral of secant x over tan squared x. So that doesn't look right. So what can we do?
Cosine over sine times sine squared over cosine squared.
So secant is 1 over cosine. And then tan squared is sine squared over cosine squared. But here it's in the denominator, so you have to flip it. So you get this. So next step here naturally is to simplify. So you wind up with this. How do you do this integral?
Sine x is
Sine
our
x
u.
negative.
U equals sine x because
The u is cosine x.
du is cos x dx, which is sitting right there. So this is just integral of u to the negative 2, which is negative u to the negative 1, which is negative sine x to the negative 1. And then there are two other ways you could write that. Negative 1 over sine x, or by definition, that's just negative cosecant x. And just to clarify, I've done it before, but let me just say it again. When I write or like this, what I'm saying to you is that you could write it any of these ways, and that's fine. Okay. And that's how you integrate expressions with trig functions in them. Usually. Okay. Those are the techniques that we're learning today. So let's sum it all up. So what did we learn today? We learned a lot. Okay. So integrals with combined trig functions, the rules. So what if you have products of sines and cosines? Well, if the power of sine is odd, what do? You factor out a sine x, replace every sine squared x with a 1 minus cos squared x, and then at the end, your u will be cos x. What if the power of cosine is odd? What if you have an odd power of cosine? You factor out a cos x. Replace every cos squared x with 1 minus sine squared x, and u is going to be sine x. What if your powers of sine and cosine are both even? You have to use those double angle formulas, the cos 2u formulas. Okay. Next, products of secant and tan. So what situations do we have? First, power of secant is even. What do? What do you take out? What do you put to the side? The secant squared x. Then you replace every remaining, I should say, secant squared x with a tan squared x plus 1, and your u is going to be tan x. What if you got a power of tan that's odd?
We factor out the 10.
You factor out not just a tan, a secant x tan x, because that's going to be your du. Then you replace every tan squared with secant squared x minus 1, and u is going to be secant x. We also looked at the situation where we have tan by itself as an even power. Turn 1 tan squared into a secant squared x minus 1, multiply, solve an integral, repeat as necessary. We saw the simplest case where it was just tan squared. Secant by itself, odd power. That was the long one. Do this by parts where dv equals secant squared x dx. What about products of cosecant and cotan? It's the same as the rules for secant and tan. Just got a negative pops into some of the formulas, so just watch that. Otherwise, try sine and cosine. Okay. And those are the techniques that we're learning today.